Hello class. I promised since we didn't meet on Thursday that I would do a video for Chapter 10 and upload it to D2L. So here we are. I wanted to start with a overview of the topics that you need to know for Chapter 10. I did put this on the board on Tuesday, but just to review and make sure everyone knows. The first thing is to be able to draw a scatter plot given data. So if you're given a set of data with input values and output values, you need to be able to draw a scatter plot. That would include knowing how to mark your x and y values by figuring out what intervals you want to go by on the x-axis and what intervals you want to go on the y-axis, and of course labeling the x and y-axis with what the data is showing. The second thing is understanding and commenting on the correlation coefficient. I'm going to go over that briefly here in a minute, but when I say comment on the correlation, that means you should be able to say whether it's a strong correlation or a somewhat strong correlation or a weak correlation. And then you should also be able to say whether it's positive or negative. Those are the two things that are important. You need to be able to say it is a strong correlation, it's a somewhat strong correlation, and then it's weak or it's positive or it's negative. The next thing is if you're given the equation of the line of best fit, so you'll be given an equation in the form y equals mx plus b, input two x values and find their corresponding y values, and then graph that on top of the scatter plot. So that's just a matter of taking those 2 points and putting them on the scatter plot the same as your other points that you put on your scatter plot. But since it's the line of best fit, after you mark those on the scatter plot, you're going to then connect them. And so then you'll have a line that goes through your data on your scatter plot that's the best fit line that you can have. You don't have to calculate that equation. That will be given to you. Same thing with the R value. You do not have to know how to calculate that. You just have to be able to comment on it. And then the fourth thing is to estimate an output value given an input value. And comment on its usefulness. So a good estimate would mean that interpolation was used and there's a strong R, and we're going to talk about interpolation in a little bit. And then the other not good estimate would be either extrapolation was used or there was a data set that had a weak R. If you don't have a strong correlation, then estimates aren't going to be very valuable. So getting away from this, and we're going to go to our slideshow for Chapter 10. I'm going to start with Section 10.1, even though we covered that in class the other day, and just go through it really briefly. And remember, we're only covering Section 10.1 and 10.2. We aren't required to cover the material in 10.3 and 10.4. So the introduction to this section starts with that in addition to hypothesis testing and confidence intervals, inferential statistics, which of course inferential statistics is where we're trying to determine something from data, make a decision or make a prediction. It also involves determining whether there's a relationship between the input and the output values. So correlation is the statistical method used to determine whether there is that relationship, and in particular we're going to be looking at linear relationships. You can do other types of analysis to see if there's some type of a curve that fits data, but we aren't going to cover that. So we're looking to find out if two or more variables are related, how strong the relationship is, and what type of relationship exists. So these are the things that you find out from the R value, and then what kind of predictions can be made. So it says that the two questions are the two variables related and what's the strength are from the correlation coefficient, but also the type of one part of the type of relationship can be determined from the R value also, whether it's positive or negative. The other thing as far as the type of the relationship that exists is you can have simple and multiple relationships. Multiple is where you have two or more independent variables that are used to predict a dependent variable. Again, we aren't going to do that. That's where more than one thing affects an output. And that can happen with almost any data. So as far as, say, a person's height. A person's height could be predicted from their age, their gender, their shoe size. There's all kinds of things that could help you predict someone's height. It's not just a simple relationship between one thing, such as your shoe size to your height or your age to your height. Not everyone that's 10 years old is the same height. And then there are the simple relationships, which is the type we're going to talk about, where we're just going to have an input value or a predictor value and an output value or a response variable. Again, the input value can be called the input value, the independent variable, the predictor variable, the X. There's all kinds of different names. The output value would be the Y, the dependent variable, the response variable. And then what kind of predictions can be made? Predictions are made every day in all kinds of situations. They list here weather forecasting, the stock market, sales predictions, crop predictions, gasoline prices, sports. So there's many different careers and many different areas in our everyday life where predictions are necessary and important. And so one of the things that is done first when you have an input that you're wondering if it affects an output is to do a scatter plot. And a scatter plot is simply just putting the points on a graph. We don't connect them because they don't make a specific line or curve necessarily, but we put the points on the graph, just plotting it, how far over for the X value, how far up for the Y value. So this is something you should be pretty comfortable with because you've done it a lot in algebra. So for instance, they gave us this example with car rental companies, and the cars would be the input and the revenue would be the output. So this would be graphed on the X-axis and this would be graphed on the Y-axis. One of the first things that you need to decide is what intervals you want to go by on the X-axis and what intervals you want to go by on the Y-axis. So for this data, they kind of used weird intervals. I would have probably just used tens on the X-axis since we have to get up to 63. I would have just gone 10, 20, 30, up to 60 or 70. And then for the revenue, since it only goes up to 7, I probably would have marked that just by ones. So here's the scatter plot. And they also mentioned that this has a positive relationship. As you can tell, it's not perfectly linear, but you can see that it's kind of trending in a linear pattern, and it's going upward from left to right. So that's positive, just like you would consider that a positive slope if you tried to draw a line through there. And then here's another example with absences and final grades. So you have your number of absences of your students and their final grade in the class. Again, this I probably would have gone by ones, and they did also. Here I would have probably gone by 10 since you have to get all the way up to 90, and that is what they did on their graph. So their graph looked like this. And so again, all you're doing is you're taking that data. For instance, the first point was 682, and they're just plotting it. So here's the point 682. Then they did that with all the other points. This, you can tell, is kind of linear. Not perfectly linear because they aren't in a perfectly straight line, but it's somewhat linear, and we call this a negative relationship because if you were to draw a rough line through there, it would definitely be going downward, have a negative slope. And so the last one that they give us for an example here is a person's age and their net worth. They picked 10 people from the 400 richest people in the world, and they wanted to know if does their age affect their net worth. If you graph this, you can see that this really doesn't lend itself well to a line. It's just kind of scattered all over. So they say that this has no relationship. I would guess if we did run some information on this, it might actually have an upward trend, but it's not very strong. It's a very scattered set of data. So this has little to no relationship. And so now talking about the correlation, you can do a population correlation coefficient, but we're not going to talk about that. We're going to talk about the linear correlation coefficient, which is computed from sample data. The particular one that we're going to use, not important that you remember this, but it's called the Pearson product moment correlation. There are other ways to calculate this R than what we do, but this is the most common, especially for an introductory type of situation. So this is how R can be analyzed, and this is what I was talking about in your notes as far as what you need to be able to do. You do not have to know how to calculate R. It's a very long equation. I'll show it to you here in just a minute. But you do have to know what it means when you're given an R. So an R can only go as high as 1 and as low as -1. If a R is 0, that means there's absolutely no linear relationship. But being positive or negative doesn't mean it's a good correlation or a bad correlation. The positive simply means it's a positive correlation, that the numbers are trending up. So as the x's get bigger, the y's get bigger. So if you're close to 1, that's a strong positive relationship, and if you're close to -1, that's a strong negative relationship. Again, though, an R of -0.95 would be just as strong as a R of 0.95 because they are both have that 9.5 value. The negative simply means that the data was trending downward, and the positive 0.95 just simply means the data was trending upward. So if you were looking at some different correlations, this correlation here would have an R of 1. This data here would have a correlation of -1 because this is perfectly linear in a positive direction. This is perfectly linear in a negative direction. These two would have a strong R. Maybe, this one might be 0.995, 97, something like that. This one would be a little lower, maybe a -0.92 versus this one would be a positive 0.95 because this is a little bit more scattered out than this is. And then these would be even lower absolute values for their R's. So this might be a, 0.85, and this might be a -0.78 or something like that. But again, this would be a lower value. It'd be negative because it's trending downward. It would be a lower value because it's more scattered out. So here's your data values, or the equation for how you calculate that R. It's a very lengthy equation. You have to do a lot of sums. You have to sum all the x's times the y's and sum all the x's. You have to sum the y's. You have to sum the x squares. You have to sum the y squares. It's kind of a lengthy computation, and we're not required to know how to do that by hand. You will be given the R on the test. In your homework, I give you a website to go to that you can put the data into to calculate the R. So you do not have to calculate the R by hand. And then they go into examples of how to calculate that R by hand. So I'm going to pause here and skip ahead. So I'm going to also stop here for just a second. They also show some hypothesis testing and the t-test for correlation. This again is not something that we're responsible for, so you don't need to worry about that. So just for interest of kind of drawing this section together, here are some different possible relationships that could occur if you do find that two variables have a relationship. The first type is that there could be just a direct cause and effect relationship, that X is causing Y. There could be a reverse cause and effect too, even though you may be checking that to see if X causes Y. It might actually be that the output that you've considered the output is actually causing the input. The other thing is that the relationship between the variables might be caused by a third variable. So there might be something else that you don't know of that's causing this relationship to occur. And in a lot of real life cases, there's a complexity of interrelationships, many things that are going on. And then the last thing is that the relationship might just be a coincidence. So let's look at a few of those. So the direct cause and effect relationship would be things like water causes a plant to grow, poison causes death, heat causes ice to melt. Out of these, this first one is actually probably more of a complexity of things because it's not just water that causes plants to grow. And then there's reverse cause and effect. They give the example, excessive coffee can cause nervousness. But this could be the reverse effect. Maybe nervous people crave coffee more. So that could be a possible reverse cause and effect. And then the third variable, if a statistician correlated the number of deaths due to drowning and the number of cans of soft drink consumed daily during the summer, you might have a significant relationship. But that would likely be because the number of soft drinks drank goes up and the deaths go up, both because there's more heat. So it's hotter, so more people drink soft drinks and more people drown, but it doesn't mean that the soft drinks are causing the drownings. And then lastly, this is the complexity of interrelationships. So you might find a relationship between students' high school grades and college grades, but there's probably many other variables involved. Your IQ, the number of hours you study, your family influence, your motivation, your age, all of those things lead to grades. It's probably not just, oh, if you get a good grade then in high school, that's then going to lead to good grades in college. And then lastly, the relationship might just be a coincidence. So for instance, if you find that the number of people who are exercising increases along with the number of people who are committing crimes, that there's no reason to believe that people exercising is causing crimes, and that there's nothing that's even causing both of them to happen as far as like a third variable that's causing both of them. It's probably just a complete coincidence. So now to the regression line. If the value of a correlation coefficient is significant, if you get a good correlation coefficient, an R that's close to 1 or -1, then the next step that researchers will typically do is determine what's called the regression line. It's also known as the line of best fit. And the line of best fit is that line that goes through the data and gets as close to as many points as possible. So for instance, here's a quick sketch of a scatter plot with some lines going through it. If you were to choose which of these lines could possibly be a line of best fit, I would probably go with this middle line. This line right here is probably a little flat. Its slope is probably a little low. This one is probably slanted a bit too high. But if you're trying to kind of go through the middle of that data with kind of the same slope, this middle line is probably the best of the three that are drawn. So in calculating the line of best fit, what the process is to determine how far away each point is from any given line, and then to try to find, if you take these distances and you sum them up, and actually they sum up the squares of the distances, to try to find that one that is the best. Again, this is a complicated process to do by hand. We're not required to do this. I'll show you when I'm done with the section what it looks like in your homework and what you can do in the homework. But on the test, I will give you the equation for the line of best fit. But just understand that that line of best fit that's calculated is the line that goes through those data points as close to all the points as possible. And here is the equation for calculating that regression line. As you can see, it is rather lengthy. It has a lot of sums. If you had very many points, this would take quite a while. So here's a continuation of a problem that we saw in section 10.1 with the car rental companies. We had used that data to create a scatter plot. Now we're going to look at, and this is something that you are responsible for, if you're given that line of best fit, could you put that line of best fit onto the scatter plot? So it says find 2 points to sketch a graph of the regression line. So they've already calculated the regression line. This is the equation for the regression line that you would get from that big long formula. Again, you'll be given this. So now that we have that, can we put that line on the graph? And the answer is yes. We could use the slope and the y-intercept, but since these are kind of odd, unusual numbers, probably the easiest way is to go back and use a more simplistic system by just picking some x's and plugging them in and calculating the y's. So in this case, they've decided to use 15, and they've plugged 15 in for x, and they've calculated it and got 1.986. Then they chose another x of 40. Again, these are up to you. You pick what values. You should just pick some values that are in between the data values that were originally given. So I'm going to go over here. For instance, the lowest one was around 8 and the highest one was around 63. So you want to pick something that's between 8 and 63 to plug into your formula. So they've picked 15 and 20 and or 40, and they've gotten these corresponding y values back. And now what you do is plot these. By the way, this little tick mark on the y in the equation just means that it's an approximation, that it's not an actual value that was gotten from the data. So they've taken those 2 points, 15, 1.986, and 40, 4.636. They've plotted them on the graph. They've done it with a different color. A lot of times when I do it, I'll do like a little star instead of a plain point, just to indicate that it was an original data point. And then connect those, and then this is your line of best fit drawn in with your scatter plot, so that you can kind of see how well it fits, and you could also look at it and make some general predictions from the graph. And then this is the second to last thing that you would be responsible for understanding and being able to do. What if I want to make a prediction? So we're going to use the equation of the regression line to predict the income of a car rental agency if it has 200,000 automobiles. So in this case, the data was in 100,000s. So 20 would be like 200,000 automobiles. So we're going to plug in 20 for X, and we calculate that, and we find that we get 2.516. So what we're saying is we're predicting from this line of regression, this equation that was given, that if a car rental company had 200,000 automobiles, that they would have a revenue of about 2.516 billion. That's not one of the original data points. It's a prediction for a company if they had that many automobiles. So how good is that prediction? So we're not going to worry about this marginal change. We're going to look at the R and the interpolation and extrapolation. So in this case, we want R to be close to 1 or -1 to consider that prediction good. If we didn't have a good R, we likely may not have even made the prediction to begin with, or even calculated the equation. But in order for it to be a good prediction, we need R to be strong. So it needs to be close to 1 or close to -1. So in the question, when I ask, if I were to ask, is this a good prediction or is this a useful prediction, if the R was high and you did not extrapolate, which we're going to talk about here in a second, it would be considered a good prediction. So you're looking for a high R and interpolation. So what does that interpolation and extrapolation mean? Extrapolation is where you make predictions beyond the bounds of the data. And when you do that, you have to do that cautiously. So I'm going to go back and look at the data set here for just a second. So in this case, I would not want to make predictions using values that were beyond 63 or below 8. If I did that, I'm kind of getting into a dangerous area where we don't know if that trend does continue forever. We just know that it looks like this between these data points. So if I were to pick a value to estimate or to make a prediction that was far beyond the original data, whether it be on the low end or the high end, that would be kind of not a potentially valuable prediction. So if you're within these data points, our slides don't use this word, but within the data points, that's called interpolation. So if I picked any value between 8 and 63 and I made a prediction with that, that would be considered a valuable prediction as long as I also had a good R. So again, remember that when predictions are made, they're based on the present conditions or the premise that the present trends will continue. But that assumption, as it says here in the slide, may or may not prove to be true in the future. Also, it may or may not prove to be true in the past. So again, that's why we don't want to go, in this case, beyond the 63 or below the 8, because those are future and past predictions. So that's it for section 10.2. I'm going to point out just a couple other things before I finish up here. So here we are in the Connect Math, and if you look at your homework assignment here for chapter 10, you can see that I have a note here that says see instructor's note at the beginning of assignments. So when you're doing your Chapter 10 homework, remember you're not responsible for finding the R or the equation of the regression line. So if you go to your assignment, the first thing that you'll notice when you pull it up, we don't usually have these, so you may not notice it if I didn't point it out. There's an instructor's note here that says you can either use your TI calculator to calculate the correlation coefficient. This is for 10-1, so we're just doing the R. If you don't have a TI calculator or you don't know how to use it, you can just take this address and copy it, and then go to a new page in your browser, paste that in, and it will take you to this calculator. And all the calculator has you do is you just put in your X values here in order, then you put your Y values here in order, and then you click on this find the regression line or find the correlation coefficient and compute it, and it will calculate it for you. So for instance, let's say my X values were 2, 5, 7, and 3. And my corresponding Y values were 20, 15, 30, and 5. Then if I want to find the correlation coefficient, I just hit compute, and it will tell me that my R is 0.6138, which would be a weak positive correlation. It's not very close to 1, and so I would say it's a fairly weak, but it's positive because it's a positive number. Okay, so then if you want to go and do the regression equation, you do the same thing. You put in your X and your Y, you hit compute, and it'll give you an equation for the line. So here's the regression equation. The only thing is this site and also your calculator will give this kind of to you backwards. I would typically write this as Y equals 2.881x plus 5.254. So this is like the slope, and this is like the y-intercept. But then it also shows it in the data, so that's real useful. So that's what you need to do on your homework. When you get to these, you can calculate the R and the equation by using this website. And on the homework, on the test, I will give you the R and the equation in the problem. And so one last thing that will just be helpful to you, not necessarily on your homework, but in studying for your final, if you come here to our D2L page and you go under exam reviews, you'll notice that I've added in a review for Chapter 10. So you'll see that this is a problem that's going to be similar to what you'll see on the test. This one says, for instance, that ice cream sales for days with different temperatures is given. So you have your X values and your Y values. Ask you to draw a scatter plot and comment on the R. Remember, that means you need to say whether it's weak or strong, and you need to say whether it's positive or negative, and this is the R value that's given. So you would plot this over here. And then once you've done that, here's your regression line. You want to place that line on your scatter plot by computing at least 2 values. So pick an X and compute the Y, and do that twice, and place that line on your graph with your scatter plot. And then it asks you to predict the sales. So take that 5 degrees and put it into the equation and predict what the sales would be if it was 5 degrees Celsius. And then comment on whether you think that's good or useful, why or why not. Remember, we're talking about being good or useful is the R strong, and was it interpolation? So I'll leave it at that, and you can work on that as part of studying for your final. We can talk about the answers in class. So just to circle around before we completely finish with the video, here's again the topics that you need to know. You need to know how to draw a scatter plot given data, understand and comment on the R. Given the equation of best fit, for the line of best fit, find 2 points from that line and graph it on your scatter plot. And then lastly, estimate an output given a value for the input, and comment on whether it's useful or not based on how strong the R is and whether or not it was interpolation or extrapolation. So hopefully that all makes a lot more sense now than it did at the beginning of the video. So that's all that I have. Thank you for watching, and hopefully this will help you to be able to do great on the Chapter 10 material.